Welcome to lecture 3 in this 6-lecture series on the foundations of DeepRL. In lecture 3, we're going to look at policy gradients and advantage estimation. How does it fit in the bigger picture of our lecture series? Well, we already looked at what are MDPs and exact solution methods, which of course only apply to smaller MDPs. Then we looked at deep Q-learning, which was our first method for solving larger MDPs. And now we're going to look at some alternative methods for solving larger MDPs, starting with policy gradients and advantage estimation. First, you might say, well, why, if we already saw deep Q-learning, why do we need yet another method? Well, today's state of affairs in deep reinforcement learning is such that there are multiple methods out there, multiple types of methods out there that are all good and have their preferred use cases. And to give a little bit of extra perspective on that, deep Q-learning type methods are very data efficient, which is nice, but are often not as stable as some of the other methods we'll look at. And also, if data efficiency is not your bottleneck, because maybe all your data is generated inside a simulator, and so data really means compute, then maybe you want to, as you think about compute, do you want to simulate more or do you want to do more Q-learning updates? And so your data can be collected very fast. Often what are so-called on-policy methods, which we'll look at in this lecture, can be more effective in terms of your wall clock time than something like a deep Q-learning method. Okay, so what are we going to look at in this lecture? First, policy gradient derivation, pretty mathematical. The whole of this lecture is actually going to be pretty mathematical. This is really about getting through the foundations of policy gradient methods. We'll look at the basic derivation, then we'll make it take advantage of temporal decomposition to be more data efficient. Then we'll look at baseline subtraction, which will reduce the variance of our policy gradient method. And then we'll look at value function estimation, which can further reduce variance. And then we'll look at advantage estimation as a way to further improve our policy gradient method and actually start bringing it quite close to actor-critic methods, and it's kind of a fuzzy boundary. You might already call them actor-critic methods once we do that. So, reinforcement learning. We have an agent interacting with the world, taking decisions. After taking an action, the world changes. We call environment here. There's a new situation the agent encountered as a consequence, takes an action again. This process repeats over and over and over. In policy gradient methods, under the hood, this agent is really going to be a policy, pi theta, which chooses an action U based on the current input S, the state or image observation of the world. And so for us, this will be a neural network taking in the current state or observation and then generating an action. And this neural network is parameterized by a parameter vector theta, which is the weights in the network. And we're trying to learn the right setting of the weights to maximize expected reward. That's the goal here. We want to maximize expected reward. Typically, this neural network will output a distribution over actions. So pi theta for a given state input will output a distribution over actions. You might say, why haven't we earlier on seen that deterministic policies can be optimal? So why also consider stochastic policies? Well, in practice, it smooths out the optimization landscape is the way I like to look at it. If policies are deterministic, two different policies are in some sense far apart. There's no continuum between them, making the optimization harder. But by allowing for stochasticity, there's this stochastic interpolation between them that's all part of the policy space, and we'll get a smoother optimization. There's another reason you might prefer stochastic policies is because as the agent is learning, it needs to collect the data to learn from. That data collection needs to somehow explore the world, and stochasticity can also help with that. So under the hood, our neural network will represent a distribution over possible actions given the state that its current input. So why a policy optimization? Well, often a policy can be simpler than a Q function or a value function. For example, a robotic grasp. You want to pick something up. It's about moving the gripper to the object and closing. But do you know exactly how long it's going to take you? Do you know exactly the graph's quality metric you can assign to what you did, that might be harder to calculate, but the right strategy might be simpler to represent and so faster to learn. A value function also doesn't prescribe actions. If all we learn is a value function and we still don't know what to do, you need maybe a dynamics model to do look ahead against the value function, but then you also need to learn a dynamics model. It's not impossible. Certainly some people do that. But it's another method and it has its own downsides there by needing all that extra machinery. How about a Q function? Isn't that enough? We can read off the correct action from the Q function. Well, it's not always efficient to solve for the argmax over actions in a current state, because that's an optimization problem in itself. And so maybe when we learn a policy, we right away can read off the solution, which could be quite convenient. So how are we going to compute our policy gradients? The methodology is called the likelihood ratio policy gradient. And this is really the core of what we're going to cover in this lecture. So a little bit of notation that's new for this lecture to keep things compact and readable. We let tau denote a state action sequence. So state at time 0, action u at time 0, and so on until state at time h, action at time h. And so tau will denote an entire such state action sequence. And then we'll say the reward for a trajectory tau is the sum of the rewards for each of the state action pairs. Because we know reward is typically associated with state action pairs or state action next state triples. And so we're going to have some new notation here, reward for an entire trajectory. Under the hood, it'll still be associated with state and actions, but just to simplify our notation. Then what we're optimizing is the utility. So every choice of our parameter vector theta in a neural network will achieve a different expected sum of rewards when we use that policy. And we can write this as the sum over all possible trajectories we could encounter, the probability of experiencing that trajectory under the policy parameterized by theta. And then, of course, that's what we weight the reward by. So this is our objective here. And so in our new notation, our goal is to find a theta, the parameters in the neural network, that will maximize u of theta, which is a weighted sum of rewards associated with each possible trajectory weighted by the probability of that trajectory. And by changing the parameters of the neural network, we're changing the probability distribution over trajectories. Some settings will favor certain trajectories. Other settings will favor other trajectories. And so we want to find a setting of the parameters in the network such that we favor the trajectories that have high reward and don't favor the trajectories with lower rewards so much. Okay, so how do we do this? We're going to again do gradient-based optimization, as is quite common in everything we've talked about and generally done by others. So u of theta is our objective. And we want to take the gradient with respect to theta. So theta lives in here, right there. Our gradient is put inside the summation. Now, well, our tau, the trajectory doesn't have theta in it. It's just a specific trajectory, but theta is over here. So here's where our gradient is going to act. But when we look at this, we could maybe think about how to compute this gradient. We'll see later how to do that. We have a sum over all trajectories, but then it's not weighted by the probability. And so what we really want is a weighted sum, because then we can sample from the distribution to compute these things. So we're going to multiply and divide by the probability of a trajectory. And now reorganizing, we now have a weighted sum. And so we have now an expectation here where we have a gradient that will compute in the back here, but then it's an expectation with respect to our trajectories collected from our current policy. So what we can do is we can actually compute a sample-based approximation. We don't have to enumerate all possible trajectories, which would be completely impossible in realistic problems. We can instead take a sample-based estimate. And so also typically what's done is this is rewritten. The grad of p over p is the grad of log p. So grad log p here. But then we can take an empirical estimate of this thing. And so our gradient estimate will be an empirical estimate of essentially an average of the gradient in the back here multiplied with reward. So this is interesting. To get our gradient estimate, we're going to use our current setting of the parameters, do a bunch of rollouts, and then for each rollout, we're going to compute grad log probability of the trajectory under the current parameter setting times the reward collected along that trajectory. Of course, this is still a lot of work to be done here, so we're not done, but that's the general structure. Now, what's interesting when you look at this is that this can be used no matter what our reward function is. What I mean with that is we don't need to be able to take a derivative of our reward function for this to work. The only derivatives taken are with respect to the neural network, well, with respect to the distribution over trajectories, which is induced by the neural network that encodes our policy. We don't need a gradient with respect to the reward function. And so you could have a reward function that is, for example, 1 when you achieve the goal, 0 everywhere else, and this will work. We're computing gradients with respect to expected rewards. And it's because of this probability distribution over trajectories that's introducing smoothness, and we can still take gradients. Okay, so now what's some intuition behind this equation? Let's say we look at this gradient here. We collected some trajectories. We look at the grad log probability of these trajectories and the reward. Well, what's going to happen? If a trajectory has very high reward, then the gradient here, so the log probability of that trajectory will be increased. So trajectories with high reward will get an increase in their probability. If now I have a trajectory with a very negative reward, we'll move the parameter vector theta by moving the gradient direction to decrease the probability of that trajectory. So we're really kind of pushing up for rewards that are positive high and pushing down the probability for trajectories where the reward was negative low. So when you think about this, it's saying shift probability mass away from trajectories with bad rewards and shift probability mass towards trajectories with high reward. It's a bit more subtle than that because probabilities have to integrate to 1. And so by pushing probability up in some places, you're implicitly also pushing it down in other places and the other way around. So there's more going on than just pushing it up on the ones that are good and down on the ones that are bad. There's more happening because of the normalization. Okay. Now, so far we've talked about entire paths and considered entire paths, but often rewards are more localized, so we might not want to do this kind of shift based on an entire path. So let's decompose the path into states and actions. So we have this grad log probability of a trajectory under the current parameter vector theta of the policy. What is it under the hood? It's a product of probabilities. It's a probability of next state given current state in action and probability of action given state. And we have this grad log product of probabilities. Log of a product is sum of the logs. So we can change it to sum of logs. Then the gradient of a sum is the sum of the gradients. So we can move that gradient inside the sums. Now, what happened here? Well, I could drop this first one because there's no theta in it. So nothing in this first term will have a gradient contribution. We're just left with this second term here. So we have grad log of pi theta, the probability of policy assigns to the action taken given the current state. And so what's very interesting here is that no dynamics model is required. All we need is looking at the policy pi theta. Interesting, right? Because we started with we want to increase or decrease the log probability of a trajectory that was experienced. And a trajectory consists of dynamics and policy. But because the parameter theta does not appear in the dynamics model, it's part of the policy, and because this is a log of a product and becomes a sum of the logs and gradient of a sum is sum of the gradients, all we're left with is this part over here. And so what we see is to increase the probability of a trajectory, we would increase the log probabilities of actions along that trajectory. And to decrease the probability of a trajectory, we'll decrease the log probabilities of actions along that trajectory, actions in specific states. Okay, so we had a gradient estimate that looked like this, grad log probability of trajectory times reward along the trajectory. And we now know that this first part here we can actually compute as a sum of grad log probability action given state along the trajectory. No dynamics model required. We can do this directly based on a neural network that represents our policy. And so now we can start computing gradients. You can roll out the current policy, then you know the rewards along each trajectory, and then you also know the state and actions along each trajectory. You can go for a neural network, do a backpropagation for each state and action experienced, compute a grad log probability of the action given state, and then accumulate the grad log probability of the trajectory, multiply with the reward along the trajectory, and you have your gradient. So at this point, we can actually do this. We can do a likelihood ratio policy gradient. Now, as formulated thus far, sure, it computes the on expectation the correct policy gradient, but it's very noisy. It's sample-based, and if you don't have enough samples, it's not going to be very precise. What are some fixes that will lead to real-world practicality? First of all, we'll introduce something called a baseline. We'll leverage even more temporal structure than we've done so far. And in the next lecture, we'll look at trust regions and natural gradients to further improve our updates. So what was the intuition again? We had this grad log probability of the trajectory times reward. And we said we're going to increase the probabilities of trajectories with high reward, decrease probability of trajectories with low reward. But actually, really we want something a little more subtle, right? What we really want is we want to increase the log probability of trajectories that are above average and decrease the probability of trajectories that are below average. Because if something's below average, you want to do less of it, and if it's above average, you want to do more of it. But here, if, for example, you have an MDP where the rewards are always positive for every state, the rewards are, let's say, between 0 and 1, then no matter what you experienced, you're always going to have a contribution here that says, let's increase the log probability of what I did, sometimes by a little bit, sometimes by a lot. And you're going to have a lot of averaging effects where the things that are, have their log probability increased by a lot start dominating over the ones where it's increased by a little bit. But really, you'd prefer to maybe, for the bad ones, closer to 0 reward to just bring the probabilities down. Can we do this? Because in that way, maybe shift our probabilities in a better way. Something called baseline subtraction will get us where we want. So we had this gradient here, grad log probabilities of trajectories times reward. Now consider introducing a baseline B. So we have grad log trajectory probability of trajectory times reward minus baseline. Say, well, you're just going to subtract something out. Yeah. How about we subtract out we have a bunch of rollouts, we look at the average reward along all trajectories, and we subtract that out as our baseline. We call it B. Then things that are above average will have an increase in their log probability of action given state, and the ones below baseline will have a decrease in their probability of action given state, and accordingly trajectories. Can we do this? Is it still an okay gradient estimate? Well, you can work through the math here at this side of the slide, but if you work through the math, what you'll see is that on expectation, this extra term will be 0. It's very interesting. Why do we even care about it? Why are we adding this minus b if on expectation it's a 0 contribution? Well, on expectation it is, but when there's finite samples, the estimate we're accumulating here, it will actually have a reduction of variance effect, which I'm not showing on the slide here, but which can be shown with the right baseline. The variance will be reduced, and you get a better gradient estimate. And the one I mentioned, the average of rewards experienced along all trajectories, is a pretty good one to reduce your variance with. So what else can we do? We now have this new thing. Our gradient estimate is now grad log probability trajectory times reward minus this baseline, which you can think of for now as the average reward along all trajectories. So what else can we do? The reward also has a temporal decomposition. We already did a temporal decomposition for the trajectory probability, which resulted in the grad log probability of action given state. We can do the same thing for reward. And then we can start thinking through, well, should all these terms participate? Is it meaningful when I think about grad log probability of an action given state that would be multiplied with a reward from the past? No, because actions I take now only influence the future. And so we can split this into rewards from the past, rewards from the future. The rewards from the past are not relevant, and if you do the careful math, you'll see that indeed the expected value coming from rewards from the past is 0, so you can just remove it without a loss in accuracy in any way. And so after you do that, we can also see that you can actually let this bias depend on the state, so you don't need to look at the entire trajectory. We can take the average of rewards experienced from, let's say, this state onwards or from this time onwards as a thing you subtract out. So we remove terms that don't contribute but only introduce variance. We get rid of that variance by removing those terms. All of a sudden we have what is the practical policy gradient equation. So what does it look like? We're going to have a bunch of rollouts, m rollouts. Each rollout has a bunch of steps in it. And we accumulate the grad log probability of the action we took in state st at time t. And we multiply it with the reward from then onwards. So rewards the action actually influenced. And we subtract out a baseline, which is what do we expect from that state onwards that we were in at time t. And so if we had a above average performance after the action, then the action probability will be increased with this update. If we had a below average performance from that action onwards, then the probability of the action will be decreased. And so we're shifting probability mass specifically, effectively for each action based on whether what we experienced after that action was below or above average. Okay, and so it's important to realize this is from this time onwards because that's the only things the action is influencing. Same for that baseline we subtract. It's how much reward you expect from that time onwards because that's the only thing the action can influence. Okay, what are some good choices for B? I've loosely alluded to this notion of average because subtracting out the average gives us a notion of are we above or below average? That's a pretty good choice, but let's step through the choices people tend to use. Constant baseline is just, you say, take the average for the entire trajectory. But you can also try to optimize it a bit more. There's something called a minimum variance baseline, which I actually have not seen people use in practice, but there's a formal derivation you can do that says that rather than just taking the average, you're going to take a weighted average. When you average the reward along a trajectory, you weigh it by the square of the grad log probability. So what does this mean? That when your gradient is very high, has a high norm, you will more heavily weigh this trajectory in your average than trajectories that have a lower gradient. And you work through the math, overall that works out to a lower variance policy gradient estimate, but of course you have to do a bunch of extra work. And practically I have not seen it in today's or last many years of implementations that people use. But maybe it's time to revisit. Who knows? Maybe it's something that you could show in some research you do that actually should be revisited and we should be using. I'd be curious if you find out that we should be using it. Time-dependent baselines are very popular. Why is that meaningful? Let's say you have finite horizon rollouts. Well, at a later time, there's less reward left than at an earlier time. And so it's a nice way to capture that. Even more precise could be state-dependent baselines. For a specific state and time, possibly, how much reward do you still expect? And that's essentially a value function under the current policy. Remember in lecture 1, we talked about policy evaluation. What is the value function for this specific policy? That's what you would use here. And we'll see more about that later, how we can do that in these larger scale problems. But you would compute a value function and then use that as your baseline. And so once you use this, you get an increase of the log probability of the action proportionally to how much its returns are better than expected under the current policy. And to me, this value function as a baseline is most intuitive because the value function is how much on average does my policy get from this state onwards? And then you're saying, well, if I did better than that, well, I chose a better than average action. If I did worse than that, I chose a worse than average action, and I'll update accordingly. Of course, you need to be able to then still learn that value function, but we'll see soon how to do that. All right, so let's take a look at that now. Value function estimation. How do we get that value function that we can use as a baseline? Well, that's where we're going to use it. There's many ways to estimate it. many ways. Here's one way. We initialize a neural network, initialize with some parameter vector phi 0, and we try to estimate the value function for a policy pi. We collect trajectories, just like we're already doing for our policy gradient estimates, and then we just do a regression against the empirical return. So this becomes a supervised learning problem. We say, hey, I have rewards that I accumulated from a certain state onwards in one of these rollouts, rollout I. So that is a Monte Carlo estimate of the value of that state, SKI. And I want my value function as represented by my neural network to be close to that. And so now I define a loss function based on squared error or maybe Huber losses to be more robust to any outliers. And I just run an optimization here. Standard deep learning framework, and you feed in effectively the sum of rewards as targets, as the outputs of the network, the state as the input, and it needs to learn to predict from state to value. And then depending on how you do this, you might have maybe small batches of trajectories and you do a small number of updates and then get more trajectories, do a few more updates and repeat, or maybe collect a large number of trajectories, do a full optimization on this. That kind of depends a bit on how you're running your algorithm. Okay, that's one way to do this. And this is often the thing you might do first when you're implementing your own policy gradient approach and you're going to estimate the value function. This is a natural first to go with because it's relatively simple. It's just a supervised learning problem. And so it's very well understood what you can expect here. But you can also do bootstrapping. Remember the Bellman equations for finding value functions, value iteration? Why not use that? In this case, it would be for policy evaluation. We know our policy V pi of S is equal to some averaging over the actions with the probability of the action, probability of next state, and then we have reward for the transition plus future value. We've done this in the exact case in lecture 1. We can also do this in approximate sense. We can collect data, then we put the data in our replay buffer, and then we say, well, let's do what is called fitted value iteration. We have targets, reward plus value at the next state, just like in Q-learning, really. We have the neural network that we're currently fitting, and then we do some gradient updates and maybe some regularization to keep our neural net parameters phi close to the neural net parameters of the previous iteration phi I. Do not jump too far from where we were before because we want to gradually optimize this because we're just getting a little bit of new data, do a little bit of an update, and get new data, do a bit more of an update, and so forth. So it's a bootstrapped approach to estimating the value function. Then, what does this give us for a full algorithm? This what some people call a vanilla policy gradient, kind of a simple version of policy gradient. You initialize the policy parameter vector theta. This is typically the weights in your neural network. And then the baseline B, which often would be a value function of some type, so maybe another neural network, but it could also be something simpler. Then we iterate. We'll collect a set of trajectories by executing the current policy. At each time step in each trajectory, we compute the return from then onwards. So RT here is the return from then onwards, discounted sum of rewards from that time onwards. And the advantage estimate. What is the advantage estimate? It's the difference between the return from that time onwards with the baseline, because we really care about how much is this better than average. Then, after we've collected all that, and we know how much we're better than average for each time onwards in each trajectory, we're going to then do some learning. We're going to first refit the baseline by having our neural network that, let's say in this case, approximate the value function. This is the supervised learning approach, the Monte Carlo approach, fitted to the rewards that we got then onwards in our rollouts, and optimize our neural network to have a better fit here. And then we can also update the policy with some gradient estimates. We know grad log really action given state times the advantage associated with that state. Okay, and of course, fitting the baseline here, the value function could be a neural net value function that depends on state that's being learned here, like we saw. That's this thing over here, Monte Carlo estimation of V pi. But of course, you could swap in this bootstrap estimate over here. You'll still have a policy gradient algorithm just as well. Often people think of the bootstrap estimate as likely being more sample efficient, but sometimes a bit less stable. And so often start with a Monte Carlo version. And then once you have that up and running, it works well. You might see if you can also get it to work with a bootstrap version in a maybe slightly more sample efficient way. Okay, now this advantage estimation, this thing that's multiplied with the grad log probability, is really key to further improving the efficiency of what we looked at. And so a lot of work has gone into that. And there are two quite popular approaches. There's advantage estimation as proposed in A3C/A2C, and there's generalized advantage estimation, which are very related, and we're going to cover now. So at this point, our policy gradient method has this grad log probability action given state multiplied with the advantage. This is the future rewards experienced minus the average we would expect the value of that state. Okay. Using the value here is kind of interesting. It's something we learn about a state, on average how well we do. But then this thing here is still a single sample estimate. And you might wonder, can we do something better there than just a single sample estimate? So how do we reduce the variance? Even for a single rollout, we can reduce the variance. And the way that's done is by introducing discounting. Another way that can be done is by introducing function approximation. So discounting, instead of using the sum of future rewards, you can use a discounted sum of future rewards. You might say, well, that's kind of weird. Haven't we talked about that as the problem definition? Haven't we said that MDP is defined by a discount factor? And that discount factor is capturing things like, well, we could earn interest rate on money if we had it earlier and so forth. That's correct. The problem definition of the MDP has a discount factor. It turns out that algorithmically, the discount factor can also be a hyperparameter you want to play with. So it's kind of interesting because you have a problem definition with discount factor, but also algorithmically, it might be something you play with. Why is that? Well, think again about what we're doing with looking at the grad log probability of an action given state and seeing how good that action was. You could say, well, maybe that action has more influence to things that are nearby than things that come much later. So maybe when I look about, is this action above average or below average, I shouldn't look at everything in the future with equal weighting. I should discount things further in the future because the action has less influence on it. Is that always true? That depends. Sometimes an action now can have a very long-term influence. But very often it's the case that actions have more influence nearby in time than they have later in time. And so this discounting here is not about the economics of, let's say, earning interest on your reward money or something. It's about discounting because the effect of actions tends to decay over time. And so by discounting, you're putting in that prior information and actually get a lower variance policy gradient, which will help you learn faster. Of course, you then also have to do it for the baseline. Where you compute the value function baseline, you have to do discounting there too to have the right difference. What else can we do? Now we have a discounted sum of rewards, but can we do more? Well, sum of rewards is just like the one thing you experienced. As I alluded to, maybe we can have some kind of value function instead here. Actually, we could. We could say reward I experienced plus value from the next time onwards. Or we could do reward now plus reward at next time plus value from S2 onwards. And we can keep doing this. There's many options. All of these could be reasonable. And so the asynchronous advantage actor critic, A3C, uses one of the above choices, which becomes a hyperparameter. For example, k equal 5, the last row here has k equal 3. K equal 5 was a popular choice in their paper. They also look at k equal 10. So what's going on here? Why using this mix? Well, in the limit, when you use the top row, if you have enough samples, you know that's exactly what you want. Once you start using value function estimates, you might be introducing some error. But the benefit of introducing them is that you're reducing variance because it's an estimate based on many past experiences that's now bundled into this value function. And so sometimes you're trading off a zero bias estimate, which is the top row, but high variance, with in the second row, you have a very low variance, but now possibly high bias estimate, and somewhere in between might be the optimal way of estimating your advantage for maximally fast learning. And that's what they did in there. In the generalized advantage estimation work, which I actually did in my lab, we saw that it's actually possible to take an exponentially weighted average between all of these in an efficient way. And so you can have an exponentially weighted average between all of these choices, which in our experience gives even a better trade-off than making one specific choice. Estimates will depend a bit on your choice of lambda. Okay, it's actually very related to, and in some ways actually equivalent to TD lambda eligibility traces from much earlier work by Sutton and Barton. Okay, so now let's take a look at our more complete approach. Policy gradient with A3C or generalized advantage estimation. What does it look like? Initialize a neural network for encoding the policy. Initialize a neural network for encoding the value of your current policy. So two neural networks. Sometimes they're the same network with a lot of it shared and then two different heads, one head for the policy, one head for the value. They can also be separate networks. That's kind of up to you. Then you collect rollouts, and these rollouts result in state, action, next state, reward, quadruples. And you store those for your update that's about to come, and gives you estimates of the Q value experienced because you have a rollout. You have a Monte Carlo estimate from a specific state and action onwards of what you experienced. Then there are two things we want to learn. We want to learn value function, we want to learn policy. First update here is on the value function. So the value function, we regress. So we want it to be close to our Monte Carlo estimate here. And then there's some regularization to make sure we don't update too much based on the latest data. And then we have our policy update, which is our standard policy gradient, sum over all trajectories, sum over all state action pairs in those trajectories of the grad log probability of action given state times, and then this is the advantage, is the reward experience from that time onwards minus the value. Now, reward experience from that time onwards could be literally reward, the Monte Carlo estimate, or we could put estimates there that we saw over here. We can use a A3C estimate or a GAE estimate for that QI hat. Then there are more variations. You could use a one-step for V, full rollout for pi that would look like this. So here's a bootstrap version of estimating V. That's okay. And then for pi, here is a full rollout, so full Monte Carlo estimate rather than a advantage estimate based on using also value functions. So many variants, but this is the general structure of what these policy gradient algorithms will look like. There's a little more we'll cover in the next lecture that can make this even more efficient to stabilize the optimization a bit more. But this is the main intuition behind policy gradient algorithms, and once they use sophisticated advantages, it often also gets called an actor-critic algorithm. We'll look at some results here. This is from the A3C paper. This is on a few Atari games. In yellow is the A3C algorithm. It's doing very well. And it's here in comparison to DQN. Remember in lecture 2, we looked at DQN. And we see this A3C approach is actually more efficient. This is wall clock time here. How long did you have to run? And performance gets better and better more quickly with A3C than with DQN. Intuitively, why might that be the case? Well, DQN puts things in a replay buffer and visits them multiple times, tries to extract and sometimes more signal from each experience, but also spends a lot of compute time doing so. Whereas A3C says, I have a current policy, I'm going to use the data I collected on the current policy, improve my policy, and then collect new data. And so you collect data in the environment based on the latest policy, which is maybe the most interesting possible data you could get, do updates based on that. And so that can give you often faster training times. Even if we maybe were to replot this in terms of sample efficiency, the sample efficiency of DQN might actually be better, but the speed of learning of this policy gradient method, in this case A3C, is faster. They also did this not just in Atari games, also did this in this kind of DeepMind labyrinth environment where the agent has to navigate, find rewards, finding apples and so forth, under the hood is now a recurrent neural network because it needs a bit of memory as it's navigating and finding rewards. Okay. Some older work actually by Russ Tedrick for his PhD work back then at MIT, he showed it's possible to have this two-legged robot learn to walk, which is really interesting that this is actually possible to do with a policy gradient method trained on a real robot learning to walk. Then in the generalized advantage estimation paper, we looked at some of these hyperparameters. So the discount factor gamma and the exponential averaging of which estimate you use, Monte Carlo versus capping it off with a value function at what time, we see that the optimum is somewhere here with a gamma of 0.98 and a lambda of 0.96. So the optimum is not at the extremes. And that's interesting because that means that you really want this variance reduction effect from using the right setting of lambda and gamma. All right, in a quick summary of this lecture, we looked at the policy gradient derivation. It's actually a pretty mathematical derivation, one of the most mathematical derivations there is in modern deep reinforcement learning. We started from a simple derivation, then introduced temporal structure, and saw that you can take policy gradients by just looking at the grad log probability of actions given state. You don't need gradients of the dynamics, you don't need gradients of the reward, just gradients of the log probability of action given state, which is in your policy, in your neural networks, that's directly accessible. We saw that we want to reduce variance by subtracting a baseline. We saw multiple types of baselines. Most intuitive and most often used is a value function baseline. So we then looked at value function estimation, the value of the current policy. We saw many ways to do that directly based on Monte Carlo estimates or bootstrapping. And then we also looked at more sophisticated advantage estimations with A3C and GAE.